All right, so good morning. Hope y'all have been having a lovely week and everything's been going well so far. You've already made it to the end of the week. There's no school tomorrow, so there's that. Exciting. Today we're gonna do two sections. We're going to do the notes and things for section 7.2 and section 7.3 about sample proportions and sample means. We'll see some examples as well of how to use these things. So there's going to be a lot of information coming at you. I do recommend that you take some notes. All right, if you have, please take notes. It helps, I promise. You do not need to try and copy everything from the slides from the PowerPoint presentation. There will be a couple of points in time where I say, hey, you probably want to have this in your notes. You definitely want to have that in your notes. So I'm just going to put that out there. Hopefully, lesson will take a normal amount of time, it'll be done in less than an hour. But because I do not see you guys tomorrow, I do have a couple extra things planned for today's lesson that I didn't do during my other classes for AP Stats on the day that I gave the PowerPoint presentation, but they shouldn't add too much time. But just so you guys are aware. All right, and apparently a third of the class decided that yesterday was the last day of school for the week, so sucks for them. Oh, there we got one more. All right, so here we go. I'm going to share my screen. We're going to start this presentation. If at any time you need me to slow down or repeat something or explain something better, please ask. I will ask throughout if you need a moment to write things down. If you do, raise your hand so that I know, and I will pause. All right, so here we go. All right, so sections 7.2 and 7.3, that is on sample proportions and sample means in chapter 7 about sampling distributions. And our goals for today is to be able to find the mean and standard deviation of the sampling distribution of a sample proportion or sample mean, and check the 10% condition before calculating the standard deviation of the sample proportions or sample means. We need to be able to determine if the sampling distribution of sample proportions is approximately normal. We need to be able to explain how the shape of the sampling distribution of a sample mean is affected by the shape of the population distribution and the sample size, and if appropriate, use a normal distribution to calculate probabilities involving a sample proportion or sample mean. That's the goal. All right. So first, we're going to talk about sample proportions, right? The sampling distribution of p hat. Ultimately, we want to know how good is the statistic p hat as an estimate of the parameter p. Remember, p is the population proportion. The sampling distribution of p hat answers this question. Consider the approximate sampling distributions generated by a simulation in which SRSs of Reese's Pieces are drawn from a population whose proportion of orange candies is either 0.45 or 0.15. We're going to see what we notice about the shape, center, and spread of these distributions. So first, we have the sampling distribution of p hat from sample sizes of 25 from the population that has a proportion of 45% or 0.45 orange candies. And looks approximately normal. The center is about what it should be based on the population proportion. It seems like an unbiased statistic. If we look at the same population, but we increase our sample size to 50, we kind of get the result we would expect, in which the distribution, right, the sampling distribution of the sample proportions is less varied, but the center still reflects a good statistic and is right about where the population proportion is. So that's good. If we change our proportion from the population to the 15%, we get these two dot plots, in which, again, we still get about something that's approximately normal for both. Right? The larger sample size resulted in a less varied distribution. Both still have centers showing that the statistic is unbiased. So that's good. All right. So these are all things that we can notice regardless, right? Based on what we've known already from section 7.1, these are things that should happen, right? Larger sample size, less variation. And our statistics are unbiased. That means we're using a proper SRS. So these give us some usable results, right? The shape, in some cases, the sampling distribution of p hat can be approximated by a normal curve. This seems to depend on both the sample size n and the population proportion. Right? It seems like as we get a larger sample size, our curve becomes a little bit more normal, right? And the population proportion tells us where the center of that shape will be, which is good. The center, mean of the distribution, is the mean of p hat, or the mean of the sampling proportions, is equal to p, right? That's also quite nice, right? It means that if this is an unbiased statistic, I don't have to do a calculation to find the mean of p hat. It's equal to the population proportion, right? Again, this makes sense because the sample proportion p hat is an unbiased estimator of p. And for the spread, for a specific value of p, the standard deviation sigma of p hat, or standard deviation of the sample proportion, gets smaller as n gets larger. The value of the standard deviation of the sample proportions depends on both n and p. Okay. And so essentially what we get from center and spread is that the mean of our sampling distribution of sample proportions only depends on population proportion that we're interested in. The standard deviation of the sampling distribution of the sample proportions depends on the sample size and the population proportion we're interested in. There's an important connection between the sample proportion p hat and the number of successes in the sample. All right, so p hat from each sample is calculated by counting up the number of orange Reese's Pieces, counted as successes in the sample, divided by the sample size, whatever size n was. So we get this random variable x representing the count of successes divided by n. And that gives us p hat, the proportion of interest. Right? In this case, it was the orange candies. You do not need to write this formula down. It is just getting us to the next point. In chapter 6, right, we learned that the mean and standard deviation of a binomial random variable x are given here. The mean of x is equal to n times p, right? The sample size times the proportion of success. The standard deviation of x is equal to the square root of the sample size times the proportion of success times the proportion of failure. Since p hat is equal to x divided by n, which is equal to 1 over n times x, we're just multiplying the random variable x by a constant 1 over n, a linear transformation, to get the random variable p hat. This is good news. So we get that the mean of p hat is equal to 1 over n times p, which is just equal to p, right? The n's here cancel. So p hat is an unbiased estimator of p. Right? The sample proportion is an unbiased estimator of the population proportion. We also get the standard deviation of p hat is equal to 1 over n times the square root of n times p times 1 minus p, which is equal to square root of n times p times 1 minus p divided by n squared, which is then equal to the square root of p times 1 minus p, the proportion of success times the proportion of failure in our population, divided by n. sample size. So we now have formulas based on what we already know from the population that will give us the mean and standard deviation of the sampling distribution of the sample proportion without doing any long calculation. Oops, sorry. And lastly, as the sample size increases, the spread decreases. This is the result from section 7.1. We know this. Bigger samples, less variation. So ultimately, we get this. This is something you want to have in your notes. Right, the sampling distribution of a sample proportion. If we choose an SRS of size n from a population size n, where little n is the sample size, large N is the size of the population, with proportion P of success, we let P hat be the sample proportion of successes. Then the mean of the sampling distribution of P hat is P. Nothing we have to do. We just copy the population proportion in for the mean of the sampling distribution of the sample proportions. Standard deviation of the sampling distribution of P hat is the square root of P times 1 minus P divided by N. Right? But we can only calculate this, or it's only a valid calculation, if the 10% condition is satisfied, meaning that our sample size is less than or equal to 10% of our population size. We must check that calculation. We must check that's been satisfied in order to get a valid standard deviation. Otherwise, we can't really use the standard deviation, and that kind of like stops the process. As n increases, the sampling distribution becomes approximately normal. Before you perform normal calculations, check that the normal condition is satisfied. This is otherwise known as the large counts condition. We need to have the number of possible successes essentially be greater than or equal to 10, which is sample size times population proportion we're interested in. And the number of failures must also be greater than or equal to 10, n times 1 minus p. That needs to be met, otherwise we cannot say that our sampling distribution is approximately normal, and we cannot perform normal calculations. Does anyone need a moment to add this to their notes? Please raise your hand. Okay, so then we'll look at an example. All right, so here's our example. We have about 75% of young adult internet users, ages 18 to 29, watch online videos. Suppose that a sample survey contacts an SRS of 1,000 young adult internet users and calculates the proportion p hat in the sample who watch online videos. All right, so before we answer our questions here, we have 75%. Right, that's a value we're interested in. The 75% here is the population proportion. That's P. All right, suppose the sample survey contacts an SRS of 1,000 young adults. Right, the SRS of 1,000, right, that is N, sample size. Right, we need these values. So we can now go into answering question number 1. Right, question 1, what is the mean and standard deviation of the sampling distribution? Right, well, our new rule says that the mean of p hat is equal to p, which is equal to 0.75. That's it. We're done calculating the mean of the sampling distribution of the sample proportions. Before I can find the standard deviation, I need to confirm the 10% condition has been met. Okay. In this case, we don't know what the actual amount of young adult internet users aged 18 to 29 is, but we can pretty much guarantee that 1,000 is not more than 10% of them. So we just have to say that, right? So we can say the sample size of 1,000 is less than 10% of all young adult internet users. So the 10% condition is satisfied. And now we can continue. It seems silly that we have to state this, but we do. You want to be specific about what you're stating. So because we have that, we can now calculate our standard deviation. Right? And our new formula says that the standard deviation of p hat is equal to the square root of p times 1 minus p divided by n, which in this case is equal to the square root of 0.75 times 0.25 divided by 1,000, our sample size. And when we do that, we get the result of 0.0137. Okay. Any questions on how I did the mean and standard deviation? Okay. So then, question number 2, check the large counts condition. Is the sampling distribution of p hat approximately normal? So we check. N times p equals 1,000 times 0.75 equals 750, which is greater than or equal to 10. N times 1 minus p equals again 1,000 times 0.25, which equals 250, which is also greater than or equal to 10. Right. This is what we wanted. That's good news. So the large counts condition is met. So the sampling distribution of p hat is approximately normal. And yes, you should capitalize the n on normal. It's kind of a pronoun in statistics. Okay. So our large counts condition has been satisfied. Last question, if the sample size were 9,000 instead of 1,000, how would this change the sampling distribution of p hat? All right, so we kind of get a little bit of logic going on here. 9,000 is 9 times the sample size of 1,000. Right. That's kind of interesting. So we get that. And the sampling distribution will still be approximately normal with mean of p hat equals 0.75. The mean doesn't change because the mean is only affected by the population proportion. We're not changing the population proportion, right? Our calculation for the mean only involves p. We don't have to worry about the sample size when calculating the mean. We do when it comes to the standard deviation. Standard deviation will decrease by a factor of 3. This is because, again, 9,000 is 9 times the sample size of 1,000. The square root of 9 is 3. Okay? And because we're taking square roots of things, that's how we get to this factor. So we get the standard deviation is our 0.75 times 0.25. That's a horrible looking 5. Divided by 9,000. And we get a new standard deviation of 0.0046. All right, and that answers question number 3. You will not always get a nice amount of decrease, but we do always know if we increase sample size, standard deviation will decrease because the variation decreases. Okay. Any questions about this example?
Can you go all the way at the top, please?
Mm-hmm. Is that all the way up to the top so you can see the problem, right?
Yeah. Thank you.
Mm-hmm. You're welcome. See, we need a moment to write things down from this example. Please raise your hand. Okay. So then we gonna jump back to the presentation. Which is here. All right. So now we're going to go to sample means, the sampling distribution of X bar, right? And X bar is the notation for the sample mean. So when we record quantitative variables, we are interested in other statistics such as the median or mean or standard deviation. Sample means are among the most common statistics. Consider the mean household earnings for samples of size 100. Compare the population distribution on the left with the sampling distribution on the right. What do we notice about the shape, center, and spread of each? Right, well, we can see on the left here, this population distribution is skewed to the right, right, and it has a center, right, or the mean household earning is as a guess, maybe around 75,000 or 80,000, give or take. I'm not entirely sure what value that is. All right. And yeah, it's unimodal, skewed to the right, center about 75, 80,000. We had, I don't know exactly what it is, but there's some quick description, right? And it varies from about 0 to 250,000. Big spread. Now, when we look at the sampling distribution of the sample means, right, when we're taking samples of size 100, we get a much different shape. Right? We get something that is approximately normal, right, with a center at about the same spot. It looks like it's in the same spot as the population mean. Right? The center of this here. Right? And it also is much less spread. All right, we have a range of about 50,000 to 100,000. So the range is much smaller, less variability. Right? So when we choose many SRSs from a population, the sampling distribution of the sample mean is centered at the population mean mu and is less spread out than the population distribution. That's what we just saw. Right, here's some facts. Sampling distribution of a sample mean. This you want to have in your notes, so you might want to start writing this down. Suppose that X bar is the mean of an SRS of size n, drawn from a large population with mean mu and standard deviation sigma. Then the mean of the sampling distribution of X bar is the mean of the population, right? Once again, this is kind of nice. We just get to take the mean from the population and plop it in as the mean of our sampling distribution. No calculations needed. Right? The standard deviation of the sampling distribution of X bar is the standard deviation of the population divided by the square root of the sample size. A little more of a simple calculation than the previous one. But also, we need to make sure the 10% condition is satisfied for the standard deviation to be valid and usable. So just like in our sample proportions, right, the sampling distribution of p hat, got to check that 10% condition before doing the standard deviation. Note, these facts about the mean and standard deviation of X bar are true no matter what shape the population distribution has. Right, shape doesn't do anything about how we do these calculations. So you need a moment to write anything down from this slide. Raise your hand, please. If we're sampling from a normal population, we get the following. We have described the mean and standard deviation of the sampling distribution of the sample mean X bar, but not its shape. That's because the shape of the distribution of X bar depends on the shape of the population distribution. In one important case, there is a simple relationship between the two distributions. If the population distribution is normal, then so is the sampling distribution of X bar. This is true no matter what the sample size is. So even if I have a teeny tiny sample size, if I start with a normal distribution for the population, I get a normal distribution for the sampling distribution. That's kind of nice. So we get this general statement for sampling distribution of a sample mean from a normal population. Right? Suppose that a population is normally distributed with mean mu and standard deviation sigma. Then the sampling distribution of X bar has the normal distribution with mean mu and standard deviation sigma divided by square root of n. Same way we saw to calculate the standard deviation on the previous screen, provided the 10% condition is met. Again, don't forget about our 10% condition. It must be checked. Does anyone need a moment to write anything down from this slide? Please raise your hand. All right. So that means we're ready for our next example. All right. So here's our example number 2 here with sample means. Right? The length of human pregnancies from conception to birth varies according to a distribution that is approximately normal, with mean 266 days and standard deviation 16 days. All right. So we have some information in our context. Suppose we choose an SRS of 6 pregnant women, and we're going to let X bar represent the mean pregnancy length for the sample. So we know that the population is approximately normal. We have a mean of 266 days and a standard deviation 16 days. Right. This also means that the standard deviation, or the mean and standard deviation here, is for the population. So we get mu and sigma here. We have an SRS of 6. So n is 6. And we're just told what X bar represents. Again, that is good practice. Identify what your variables represent. X bar is the mean pregnancy length for the sample. Right. Question 1 wants to know, what is the mean and standard deviation of the sampling distribution of X bar? Well, the mean, once again, the mean of X bar is equal to population mean, which is 266 days. And that's it. We've completed the calculation for the mean of the sampling distribution of X. Once again, we have to confirm the 10% condition. And again, this seems kind of maybe unreasonable, but it absolutely is reasonable and necessary, right? To say that the SRS of 6, right, the sample size of 6 pregnant women is less than 10% of all pregnant women. Right? We just have to say it. All right, so the sample size of 6 pregnant women is less than 10% of all pregnant women. So standard deviation of X bar is equal to population standard deviation divided by the square root of n, which is equal to 16 divided by square root of 6. And we get 6.532 days. Excellent. And now we're done with question number 1. Is there any questions about how I did the mean and standard deviation for this part? Número 2. We need to find the probability that the mean pregnancy length for the women in the sample exceeds 270 days. Right? To do this, we want to find the probability that X bar is greater than 270. That's the problem we're trying to solve. All right. We need to confirm that this can be done. Right. Now, we know that our population is approximately normal, so our sampling distribution is going to be approximately normal. So we can calculate this using our normal distribution. Good news, that means we use table A, we standardize our score, and we do all those fun steps. So first, we're going to standardize 270. So we get z equals 270 minus 266 divided by 6.532. And we get a standardized score of 0.61. That tells us that the probability of x bar being greater than 270 is equal to the probability of z being greater than 0.61. Okay, this is equal to, because remember, table A only tells me proportions less than or equal to a value of z on my distribution. It does not tell me greater than, so we can use the complement rule. And this tells me the probability that this probability is equal to 1 minus the probability of z being less than or equal to 0.61. And so I go to my table A, which I keep forgetting to have open. All right, and we go to the positive side of table A, we find 0.6. And that's right here. Come on, why are you not drawing for me? Oh, come on. There we go. We get 0.6, and then we find the 1.01. So there. And they intersect right here. 0.7291. So that means this is equal to 1 minus 0.7291, which is equal to 0.2709. And that's what we were looking for. This is the probability that selecting 6 women whose mean pregnancy length exceeds 270 days. Right. And we're done. Is there any questions about how I solved these two problems?
I have a question, but for the other one,
Okay.
I don't. For the 10%, do we like? How do you know if it's less or greater than 10%?
So in some cases, it's just that it's something that should be true, right? So like for this example with the pregnant women, it's somewhat obvious that there's going to be more than 60 pregnant women at any point in time in our population, right? Now we could, if we really wanted to, we could go find numbers. That takes more work than we want to put into this type of calculation as far as the class is concerned. So it's not provided, and it logically makes sense that our sample size is less than 10% of the population. Then we just need to state that fact. If we are actually provided with the size of the population, then we can check, right? Then we can actually use numbers and show like, well, hey, 10% of the population would be this number. Our sample size is obviously less than that, so the 10% condition is satisfied. You know, these two examples aren't ones that we can do that with, but we'll see an example later that we do. Does that answer your question?
Yes, thank you.
You're welcome. All right, so we're going to jump back to our presentation. That one. All right. So lastly, with our sample means and sampling distribution of x bar, we have the central limit theorem. Right? And this is to help us with the case that our population is not normal. Right? Most population distributions are not normal. Right? What is the shape of a sampling distribution of sample means when the population distribution isn't normal? It is a remarkable fact that as the sample size increases, the distribution of sample means changes its shape. It looks less like that of the population and more like a normal distribution. This is actually what we saw in the histograms for mean incomes. Right? That started our section on sample means. When the sample is large enough, the distribution of sample means is very close to normal, no matter what the shape of the population distribution is. As long as the population has a finite standard deviation, meaning like we know what the standard deviation is, and we know that it exists, and it's an actual number. If we draw an SRS of size n from any population with mean mu and finite standard deviation sigma, the central limit theorem, CLT, says that when n is large, the sampling distribution of the sample mean x bar is approximately normal. We will define what n being large enough is in the next slide. Right, but this is good news, because now, as long as our sample size cooperates, we can use a normal distribution for our sampling distribution to do calculations, even if the population isn't normal. Okay. So even when the population distribution is very non-normal, the sampling distribution of the sample mean often looks approximately normal with sample sizes as small as n equals 25. And this is what we want to write down in our notes. Normal/large condition for sample means if the population distribution is normal, then so is the sampling distribution of x. This is true no matter what the sample size n is. If the population distribution is not normal, the central limit theorem tells us that the sampling distribution of x bar will be approximately normal in most cases if n is greater than or equal to 30. So if our sample size is greater than or equal to 30, we can say, well, by the central limit theorem, this sampling distribution will be approximately normal, and we can now use normal calculations. All right. So that is our cutoff line. Right, so for sample size being large enough for a sample means, that is 30. Central limit theorem allows us to use normal probability calculations to answer questions about sample means from many observations, even when the population distribution is not normal. Can you please raise your hand if you're writing stuff down and need a moment to finish? So then side-by-side comparison here, we have sampling distributions, proportions versus means. Right? For sample proportions, right, the mean of the sampling distribution for the sample proportion is equal to the population proportion of interest. The standard deviation of a sampling distribution of sample proportions is equal to the square root of the population proportion times 1 minus the population proportion divided by the sample size of n, as long as the 10% condition is satisfied. And as n increases, the sampling distribution becomes approximately normal. Large counts condition must be satisfied to do normal calculations. Right? And again, that is having at least 10 successes and at least 10 failures. Right? So np and n times 1 minus p both must be greater than or equal to 10. When dealing with sample means and sampling distributions of sample means, right, the mean of the sampling distribution of sample means is equal to the population mean. The standard deviation of the sampling distribution of sample means is equal to the standard deviation of the population divided by the square root of the sample size n, provided the 10% condition is satisfied. If the population distribution is normal, then so is the sampling distribution of x bar. The central limit theorem says that when n is large, the sampling distribution of the sample mean x bar is approximately normal. Right? This applies to cases where the population distribution is not normal. Right. So I'm going to show you guys a couple of examples for proportions and means, one for each of these. It's different than the first two examples we saw, and then we'll wrap up. All right, so this has already been worked out. I'm going to walk you guys through what this is. All right, so this is a problem from the textbook. All right, we have a sample survey that interviews an SRS of 267 college women. Suppose that 70% of college women have been on a diet within the past 12 months. What is the probability that 75% or more of the women in the sample have been on a diet in the last 12 months? All right, and to do this, we need to calculate the mean and standard deviation of the sampling distribution of p hat, check the 10% in large counts conditions, and then if the conditions are met, we can use the normal calculations to find the probability. So first, right, we label the things we know. I just kind of data dump, right? N equals 267, P, population proportion, is 0.70, P hat is equal to the proportion of women who have been on a diet from the sample survey. The mean of P hat is 0.7, the same as the population proportion. Right? 267 is less than 10% of all college women. Right? So the 10% condition is met. And again, this falls into the case of, well, we don't know exactly how many women are in college at any point in time, but it's pretty safe to say that 267 is less than 10% of that number. So because the 10% condition is satisfied, the standard deviation of p hat is equal to the square root of 0.7 times 0.3 divided by the sample size 267, which is equal to 0.028. Okay, so we now have the mean and standard deviation. Since n times p equals 267 times 0.7 equals 186.9, and n times 1 minus p equals 267 times 0.30 equals 80.1, are both at least 10, the large counts condition is met, and the sampling distribution of p hat is approximately normal. That means I can now treat this as a normal distribution and use table A and what we know about normal distributions to find our probability. We want to find the probability that p hat is greater than or equal to 0.75. So we standardize 0.75, right, and get the z-score 0.75 minus 0.70 divided by 0.028 equals 1.79. Probability of z being less than or equal to 1.79 is 0.9633. We find this one because we need to use the complement rule, because our original calculation is asking for greater than or equal to. Table A doesn't give us that number. All right, so we convert this to 1 minus p, the probability of p hat being less than or equal to 0.75. That is 1 minus 0.9633, which is equal to 0.0367. Right here we see where we found our number on table A, 1.79, 0.9633. We get that value here. So to answer our question, there is a 0.0367 probability that 75% or more of the women in the sample have been on a diet within the last 12 months. Right, so the work that comes before the statement of our answer is the evidence that our answer is correct. Right, we have to show the work. Is there any questions on this example? Anything I can clarify? And that's kind of like how we can use what we've learned in section 7.2, this is sampling proportions, to answer a question. The next example. Right, the number of flaws per square yard in a type of carpet material varies with mean of 1.6 flaws per square yard and standard deviation of 1.2 flaws per square yard. Population distribution cannot be normal because a count takes only whole number values. A normal distribution is continuous, and it is possible to have all values. An inspector studies a random sample of 200 square yards of the material, records the number of flaws found in each square yard, and calculates X bar, the mean number of flaws per square yard inspected. We want to find the probability that the mean number of flaws exceeds 1.8 square yards. All right, and again, so to do this, we need to calculate the mean and standard deviation of the sampling distribution of X bar, check the 10% condition, and if the CLT can be applied, central limit theorem. Then, if those things are met, we can use normal calculations to find the probability. So again, at the beginning, I just have the provided information. The mean is 1.6 flaws per square yard. Standard deviation is 1.2 flaws per square yard. My sample size n is 200 square yards. X bar is the number of flaws per square yard in the sample. So the mean of X bar is 1.6 flaws per square yard, the same as the mean from our population. And again, we're assuming 200 square yards is less than 10% of all the carpet. So the 10% condition is met. This is, again, just a safe bet that a carpet company carries more than 2,000 square yards of carpet. So then we can find a standard deviation of X bar, which is equal to the standard deviation of the population, 1.2, divided by the square root of the sample size of 200. We get 0.0849 approximately. Since n equals 200 square yards is greater than or equal to 30, right, the central limit theorem is satisfied, and the sampling distribution of the sample mean X bar is approximately normal. And we do our calculations here. So again, I want to know the probability that X bar is greater than 1.8. I use the complement rule and do 1 minus the probability of X bar being less than or equal to 1.8. I standardize 1.8, 1.8 minus 1.6 divided by 0.085. Right, I rounded that. And we get 2.35. We get 1 minus the probability of Z being less than or equal to 2.35 by finding 2.35 on table A. We get 0.9906. 1 minus 0.9906 equals 0.0094, a little less than 1%. So there's a probability of 0.0094 of finding that the mean number of flaws is greater than 1.8 in a random sample of 200 square yards of carpet. And we've answered the question. What questions do you guys have? Is there anything I can clarify? Okay. So then, ultimately, we've covered our objectives. We can find the mean and standard deviation of the sampling distribution of sample proportion or sample means and check the 10% condition before calculating standard deviation of the sample proportions or sample means. We can determine if the sampling distribution of sample proportions is approximately normal, large counts condition. We can explain how the shape of the sampling distribution of a sample mean is affected by the shape of the population distribution and the sample size. If the population is normal, the sampling distribution of the sample mean is normal. If the population is non-normal, then if the CLT, the central limit theorem, is satisfied, the shape of the sampling distribution of the sample mean is also normal, but that means sample size must be greater than or equal to 30. If appropriate, use normal distribution to calculate probabilities involving a sample proportion or a sample mean, and we saw examples of that. And that brings us to the end of the slideshow. So, lastly, looking at our course. Okay. The calendar here, February, right? If you notice, tomorrow, no school, Monday, no school, right? We get a nice 4-day weekend. Please remember that. Here is a link to the presentation from today, the PowerPoint. I will add links to our example problems, or you can just go to the 9th or the 10th. These are the 4 problems we saw today in class. And I'll upload the recording when that's ready. Also, if we go into Chapter 7 module, the solutions to all practice problems have been posted. And so you can now, if you've been doing the practice problems, you can check your work. And I have this Desmos activity. We did this in class with my periods 1, 3, and 5 yesterday. Unfortunately, we will not be able to do that today. And we won't see you tomorrow. So if you would like to do this activity, you will get extra credit for doing so. So if you're looking for some extra credit, this is something you can do. Right? And this again should help just clarify some of the information we've been covering in chapter 7. Okay, so again, if you're looking for some extra credit, it's right here. The chapter 7 assessments should be ready before next week. We'll be wrapping up chapter 7 next week, in which case you'll be able to do the assessments. Okay. And then grading period ends next week. So keep that in mind as well. If you have not yet done the chapter 6 assessments, that will hurt your grade on the end of the grading period. Right? I got to post grades. If you haven't completed that stuff, it's going to go in as like a 0, and that's going to hurt if you haven't done it. But keep in mind, once you do it, 0 will be replaced with whatever grade you get. There's no penalty for late work. Right? Is there any questions about the lesson or the course? Anything I can clarify? All right. Then with that, I hope you guys have a wonderful 4-day weekend. Get some time off, relax. Hopefully you get a chance to step away from school stuff over that 4-day weekend. If you do have any questions, you need help with anything you're doing in my course, please reach out and let me know. But other than that, have a great weekend, and I will see you guys next Thursday. No, wait. Yeah, next Thursday. Yeah, no tea lesson. No school Monday. All right. So have an awesome weekend.